Okay, so today we're going to be reviewing a an experiment proposed by quantum physicist Gao, Sean Gao, um, and basically it's a variation on the Aharonov-Bohm effect. And what he's proposing is that um, if you can make the distance far enough from the um, interference field for the detector of a like double slit, and then from the solenoid. So it's completely impossible for the magnetic potential, the electrical potential, to have any kind of magnetic flux effect on the quantum interference field because you turn on the interference field detector, or you turn on the solenoid before the interference field is actually created by the detector, but um, you keep the distance far enough away so that there's no way the potential of the solenoid, the classical potential, can affect the quantum interference field. So by doing this, the relativistic physics in quantum field theory assumes that there can be zero effect from the solenoid potential on the interference, the quantum interference that's detected by the electron. But the Aharonov-Bohm effect has proven already that the interference field is from the classical potential interacting with this non-local. But the question is it interacting due to switching on the solenoid? So the point of this experiment is to prove that there is a non-local field from the future, a quantum potential force from the future that is already in the classical solenoid, because there's absolutely no way that the switching on of the solenoid has time to affect the quantum interference field. There's no way they can classically interact at all. So normally, what you're having here is I'm just going to read from my blog, but the experiment as proposed, what it's doing is it's emphasizing what Roger Penrose calls the quantum measurement problem. So essentially, you use the Schrodinger equation to have a prediction, but then when you actually make the measurement, that's based on essentially like collapsing. And when that commutator collapse, then there's zero effect of the commutator because it has to be a symmetric space-time. And so let me see if I can. So this is something that's always the quantum measurement problem is always why I've kept reading quantum mechanics books, because obviously, like Roger Penrose says, there's a problem with quantum physics. So the solenoid is switched on during the electron's interferometric passage. And so the classically retarded field from the past of the solenoid cannot reach the electron's path before the interference is complete. And classical physics with relativity says there's no way that the electrical potential can then affect the interference field. But the non-zero Aharonov-Bohm phase shift still persists. And so the only way this is possible is because of the influence of a future from the future of a force that's non-local, and it's not dependent on turning the solenoid on, because the solenoid there's no way that the solenoid can interact with the interference field of the quantum detection. So this means that the quantum potential phase shift is being continuously generated during the traveling of the electron, and it's not immediately generated when the electron beams overlap between the solenoid and the interference field. Um, and so, in this sense, that what is considered to be classical causality is violated, and the future is influencing the past. And so Gao calls this the forward causal disconnect condition that this experiment is creating. Whoops, I gotta go get the phone.